This class is about statistics for test analysis. And the first thing I've got to say, you can see the screen there, that everyone is terrified of statistics. And this is particularly true of people studying applied linguistics, because most come from a background in languages or humanities, sometimes social sciences, but even in social sciences, usually there's no background in numbers and stuff. Now, let me tell you straight away that this is nowhere near as bad or scary as it looks when you see these formula and stuff, like the ones you can see here in the top right of the screen. And it's kind of my job to make this accessible to you in a way that you can use so that you can do some statistical analysis with your tests, so that you can read and understand the statistical material that occurs in articles on language testing and assessment, and indeed in most empirical research in applied linguistics. And believe it or not, it's dead easy. I'm going to explain some of these formula to you. I'm going to show you how they work, and I'm going to show you how to use the software so that the number crunching becomes really, really easy. But I'm going to show you how the formula work as well. So let's kick off, and just to pick up from where we finished off previously, and that's by looking at the test design cycle. And I said that we had gone round the elements of the design cycle while we were looking at units from the course book from test purpose onwards. And in this, the statistical analysis, we're looking at, to some extent, the piloting, but chiefly field testing. And field testing and piloting takes place once we have a large enough group of items or tasks that we have designed for a test, and we want to find out how they work, including how difficult they are, whether or not they separate out the students across a scale, so that we know who are the better students, who are the weaker students, on the construct of interest that the test is designed to assess. You will remember that the word discrimination is actually a good thing in testing, and we do actually have things called discrimination indexes that tell us the extent to which our test and our items on the test are separating it out. So we're looking then in the test design circle at these last elements. We've talked about inference and decisions as well, but we're looking at these last two elements, which are piloting and field testing, where we collect that empirical evidence. Now, before we start on looking at some of the statistical tools that we need, there are three kinds of variables that I have to explain to you, and I'm using here on the left the images that come up in a program called the Statistical Package for the Social Sciences. And I'm using these particular images because you can download this program from the university website, and you can get a license from the website to run it on your machine at home. And I'll be demonstrating in a little while how to do some of the calculations on SPSS, that's the statistical package for the social sciences. So, first up, a scale variable means that we count things, and we count them as if it were a ruler, and that's why you can see here the image of a ruler. And with a scale variable, we assume that, like a ruler, each unit has an equal interval, is equal to all other units, and that there is an equivalent distance between one unit and another. So on a scale, a ruler that has inches, the distance between 1 and 2 inches is the same as the distance between 11 and 12 inches. And to measure 1 inch, it doesn't really matter which bit of the ruler you use. And it goes up, and whether you're using centimetres or inches or whatever other unit of measurement you're using, it is equal and equivalent. Now, we assume in language testing that when we give a test, the score that we give to learners taking our test is a scale. We assume it's an equal interval scale, like a ruler. Now, I'm not going to discuss that at the moment, but I will throw this out for you to think about. Is that true? Are we really measuring on an equal interval scale, and what does it mean to claim that we are? Okay, the next one is ordinal. An ordinal means that things are ordered. So better or worse, least or most preferred. So I could say to a learner, which kinds of tasks do you prefer the most? And they could sequence them, the things they like doing most and the things they like doing least. So there is a sequence. But let's say a learner says, well, I like doing speaking tasks where I talk to my partner. After that, I like doing speaking tasks where I'm in a group. And after that, I like doing quiet reading. The distance between quiet reading and speaking in a group is not the same as speaking in a group and speaking to one's partner. They're sequenced but not equal interval or distance. So that's ordinal. The last one that we get in packages like SPSS is nominal. And for a nominal variable, each observation falls into one and only one category, which is why we have these separate circles. So in the US, for example, they have two political parties, really. The Democrats and what's the other one? The Republicans. Yes, of course, you can tell I'm not American. The Democrats and the Republicans, and you go and you say, are you Democrat or Republican? And they're not going to say both, because they can't vote twice. So it's Democrat or Republican. You are in one box or you're in another box. And we can think of lots of other categories in life where we would say that this is nominal or categorical data. So do you live in a city, a town, or in the countryside? That's 3 separate boxes. You notice that we've got to define what a city is, we've got to define what a town is, and we've got to define what the countryside is. Because if there is any uncertainty about the divisions between those, then we don't have clear categories. Okay, I'm going to come back to that in a little while, but remember what I said earlier. The assumption is that when we get language testing data, the data is on a scale. Right, section 1. We're going to talk about descriptive statistics, and that's the mean, or the average, as you're probably more familiar with it, and the standard deviation. And the mean and the standard deviation are the two statistics which we report for every single test, and indeed whenever we're collecting data from groups of individuals where we're counting stuff, the mean and standard deviation are the two statistics that we always have to give. And there's a reason for this. We make the assumption that when we have scaled data and we're counting things, that the data is normally distributed. Now, on the screen you can see a curve of normal distribution. And the curve of normal distribution means, I shouldn't say that means because I might confuse it with the mean score, but the mean score is the average, so it's the one that occurs right in the middle here, okay? And the curve of normal distribution assumes that most of our observations will fall at or near the mean. As we move further away from the mean, or the average, the number of observations will become fewer and fewer and fewer. Now, this is not a difficult concept. Let me give you an example. One of the main buildings on the campus at Leicester is the Charles Wilson building. Don't know if you've ever been there, but it has student services in there and quite a few other things, cafes, restaurants, a few lecture theatres, but not many of those. It's mostly restaurants. And if I were to go and stand on the steps at a random time of the day, and I decided that I would count the next 100 people coming into that building, and for each one I asked the person, can I measure how tall you are? Now, let's assume I'm only doing men for the moment, because men and women have different average heights. Let's assume that I only do men. And let's say that I find, after measuring the height of 100 men, that the average height is 5'10". Now, most of the people that I measure will be 5'10", and around that, say 5'8" to 6 foot, we would get about 64.26% of all the observations. Right? So the distribution around the mean, most of them would fall in this area. Now, in counting the 100 people, I might come across one person who's like 6'5", and that person is going to be right up here. So he's going to be like in the top 1% of height. And if I come across one person like that in 100, that would be quite unusual. Similarly, I might come across one person who's 5'2", and they would be in the bottom 1%, because we don't come across many men who are that small. And that's what a curve of normal distribution is. And surprisingly enough, most of the things that we count in life follow this pattern. So, for example, if I decided that I was going to go into a school and pick all 16-year-olds in the school and measure their feet. Most of them would be of average size for a 16-year-old. Some of them would have large, very large feet, but a very small number. Some of them would have very small feet, but a very small number. Surprisingly enough, one of the places where this was first applied was in the hat industry. And there is actually data from the 1800s of hat manufacturers measuring the size of people's heads to decide how many hats of each size to make, so that when people came into the shops, they didn't stock too many hats for people with really big heads, or too many hats for people with very small heads. And most of the hats were in this central area around here. And that makes a lot of sense. So you can see how it works. The interesting thing here, of course, is that, as I said earlier, men and women have different heights. You know, the average height is different. So if I were to count 100 men and 100 women and get the average height, I would then be able to do a statistical test to see if the average for men and the average for women, when I found what the difference was, whether or not that was likely to occur purely by chance, or whether women generally have slightly smaller heads than men. And this is the basis on which lots of social research is done. So if you make a claim that people from certain ethnic minorities earn less than the majority ethnic population in a country, you could actually collect the salaries, the salary data for different ethnic minorities and for the majority population, and then that's the salary, of course, is scale. Okay, your membership of an ethnic group is nominal, and you then test the difference between the two means. So before we move away from this diagram, you can see that we know that 64.26% of all observations on anything that is normally distributed will fall between -1 and +1 standard deviations, because that's the distribution. Once you get up to 2 standard deviations, you're covering a much larger percentage of the population. And above 2 standard deviations is only 2.27% of the population. So this is how we know, with normally distributed data, what the average is and the standard deviation. And so when you see in research the mean or the average and the standard deviation, these are the two numbers that describe the average and the distribution of the data that has been collected. Now let's look at the mean first. This is the average. And the definition of the mean, here we have the formula on the left hand side. And I will read this formula to you and then I'll explain it. Here is x. And x we normally use for an individual score. When we put a bar over it, it stands for the mean or the average of all of the x's. So in this case, in a test, student 1 gets, say, 10, student 2 gets 12. Right? So we've got two x's, 10 and 12, and the average, 10 plus 12 divided by 2, I hope is 11. Okay? because off the top of my head, I've never really actually been very good at mental arithmetic, even though I'm pretty good at statistics. So X bar is the average or mean. This symbol here, sigma, that's the Greek letter sigma, the capital letter, and that stands for the sum of. In other words, add them all together. And X is each individual score. Divided by, and N always means the number of observations. So if you're reading a paper and it says the N size was 50, it means there were 50 participants in the study. So the mean, or the average, is calculated by adding all the scores that you get on a test. That's the sum of X, and dividing by the number of scores. And that defines the central point on the curve of normal distribution. So that frightening looking formula, X bar equals the sum of X over N, is really so simple. All we do is add it up and divide by the number of things we've got. Okay? So that's the average or the mean. Now, here is an example. I've got 25 scores. So N equals 25, because there were 25 test takers taking the test. Now, when I add all of their scores up, the sum is 293. So when I do the division, I get the mean is 11. Now, look at the table here. I like doing things in tables like this because it helps to make everything clear. So don't worry about these two columns on the right yet. I'll come to those in a moment. Step by step to understand how this works. So the column on the left is the scores that each of my 25 people got. Student 1 scored only 1. This is a test with 30 items, okay? 30 multiple choice items. Person 1 just got 1. Person 2 only got 1 right. Poor people. And they go down, you see. One person got 5. 2 people scored 6. 1 person scored 7. 1 person scored 8. 2 people scored 10. 3 people scored 11. 2 scored 13. 1 scored 14, and so on. 1 person scored 28 out of 30. Now, you can see already, just by looking at those numbers, that most people are scoring in the middle here, okay? Very few scores at the bottom, very few scores right at the top. So, this is normally distributed. When I add all of these scores up, the sum of X, it's 293. There are 25 scores, okay? So when I divide 293 by 25, the answer is 11.7. I've actually rounded that to 1 decimal place for this table. But in applied linguistics, we normally report figures to 2 decimal places. But I've rounded it for simplicity here to 1 decimal place. I think it's about 11.748, something like that. It'll be on another slide, so we'll get there. But I've rounded it up here to 11.7. So the average, the mean, is 11.7. So in the middle here, 11, no one actually got 12. 2 people got 13. Right. Okay, so they're at 11, 11 and 13, they're the closest to the mean in the middle of the distribution. So that's an example of how to calculate the mean. I'm going to show you how to do it on SPSS in a little while, and of course there are lots of websites. I mean, if you just type into Google mean and calculate mean standard deviation, you'll come up with hundreds of web pages that will do this as well. Now, here's the formula for the standard deviation. Now, this looks much more complicated, but you'll see that it's just as easy as the mean. Now, I will read the formula to you. The standard deviation equals the square root, which is what this sign means, of the sum, here we've got sigma again, the sum of x, and you know what x is now, it's the score, minus x bar, and now you know what x bar is, it's the mean, squared, divided by n, and you know what n is now, it's the number of observations, minus 1. And the standard deviation tells us how the scores are distributed along the curve. Okay, and the distribution may be fairly small, or the scores may be much more spread out. It tells us, this is useful for class information, because it tells us how, if it's a very small standard deviation, then it tells us our students are fairly homogeneous on whatever it is we're testing. If the scores are spread out, then the class is much more heterogeneous. Now, you already understand some bits of that formula, but let me show you how it works, and then I'm going to show you how to do it on a computer. So you'll never have to calculate it by hand, but I want you to understand how it's done anyway, so that you see how the standard deviation and the mean relate to the curve of normal distribution. Okay, so let's start off again. Left-hand column, I've got my scores. I've got n equals 25, and I've got x bar, the mean, is 11.7. The sum of all the scores is 293. Now, the first thing that you'll come across is something called the range, this first bullet point at the top. 1 is the lowest score, and 28 is the highest. So we have a range of 27. That's 28 minus 1. Okay. Now, given that we have score a test with 30 items, that range is quite large. So we would expect a fairly large standard deviation. Now, I told you to ignore the other columns when we looked at this table before. Now I don't want you to ignore them. Let's move on from the scores to x bar. Now x bar, the mean, we know, is 11.7. And this column is just x bar, and you can see it's 11.7 all the way down. And that's because it's the average and it doesn't change. The next column to that is x minus x bar, which, if you look at the formula for the standard deviation, is this bit here, x minus x bar. All right? So x minus x bar means the score minus the mean. So 1 minus 11.7 is minus 10.7. And that tells us that this is 10.7 scores, or units of measurement, below the mean. Easy, isn't it? So if someone gets 10, 10 minus 11.7, the average, means that it's minus 0.7. So they're 0.7 units below the mean. When you go above the mean of 11.7, someone gets 13, 13 minus 11.7 is plus 1.3. So they're 1.3 units above the mean. Okay? If someone gets 28, then 28 minus 11.7 is 16.3. So they're 16.3 units above the mean. Now the interesting thing here is that if you add all of these up, all of the minuses will be exactly the same as all of the pluses. So if you sum that column, you will always get 0. And that is why in the middle of the curve of normal distribution we say it's 0 standard deviations from the mean. So if you get exactly the mean as a score, then the standard deviation at that point is 0. It does not deviate from the mean at all. Wonderful, isn't it? Okay, we now move on to the next bit, which is the sum of x minus x bar squared. So the first thing we do is we square x minus x bar, and this is the last column. Now the square just means multiply it by itself, and you will see on most calculators, you will have a calculator on your iPad or your iPhone or whatever, and you'll see that there is a symbol, the subscript 2, right, which just means the square of whatever it is. So 10.7 squared, 10.7 multiplied by 10.7 is 114.5. Okay, when we go down to something that's very close to the mean, like 11, 0.7 squared is, I've rounded this to 1 decimal place, is so close to the mean that it's 0 when rounded to 1 decimal place. So in this case you can see that the closer to the mean, the smaller the number, just as it was in the x minus x bar column, and the further away from the mean, the much larger the squared number. Okay, so you take 10.7, square it, and you've got 114.5. So let's go through that once more. The score is 1. The average is 11.7. 1 minus 11.7 is 10.7. 10.7 squared is 114.5. I then add up all the numbers in this last column, and the sum of those numbers is 1345.5. So the standard deviation now is the square root of 1345.5 divided by n minus 1. N is 25. 25 minus 1 is 24. And you will see that the standard deviation comes out at 7.49, which I have rounded up to 7.5. But in a research study, you would actually report it as 7.49 to 2 decimal places. Now, this is the standard deviation, and it tells us how far the scores, how the scores are distributed around the mean. So, come back to our example again. We saw that the range is 27. The standard deviation is 7.5. Therefore, one standard deviation either side of the mean is 11.7 plus or minus 7.5. Remember, 68.26% of the scores will fall in that central zone on the curve of normal distribution. So 28.26% of scores fall between 19.2 and 4.2. That is 11.7 plus or minus 7.5. And we know that this will happen if we've piloted our test properly for all future administrations of the test. This is a very wide distribution, right? You know, that's huge. You know, it's it covers most of the scale, particularly at the bottom. You know, you're running out of points here, and I wonder, in the case of this particular test, I think it's actually probably too difficult, and there probably aren't enough easier items for the lower level students. So that's the standard deviation, and this is what we report. Now, just so that you understand this bit about the 68.26% of scores fall between 19.2 and 4.6, because that's the mean plus or minus the standard deviation, look at the distribution on this test against a curve of normal distribution. The average, which defines the central point on the distribution, on our test is 11.7, all right, and that's 0 standard deviations, because the x minus x bar column always adds up to 0. 11.7 minus 7.5 is 4.2. 11.7 plus 7.5 is 19.2. So 68.26% of all of our learners we would expect to score between 4.2 and 19.2. That person who scored 28 on our test is right up here, okay? Literally in the top 0.5% of all students who might take our test, assuming that the sample we used to pilot our test was drawn from the population of students whom we would expect to take the test in the future. So that explains the standard, the mean, the standard deviation on one particular test. Now, what I'm going to do next is to show you how that works on a computer program. Okay, here is the test, and this is the data view of SPSS, which, as I said, if you go to the university's website, the IT Services website, or Google it, University of Leicester download SPSS, you'll be able to find it. You can download the program and then you can apply through the website for a license to run this program. But these statistics, there are lots and lots of websites that will do stuff like this as well. Now, from my table, you can see student 1, students down the left. These are my cases, or students or test takers. But in SPSS, they're called cases. 1, 2, 3, 4, 5. These are people. So the first person got 1, second person got 1, third person got 2, and so on. Here are my 11s, the ones near the mean. And as I go down, n equals 25. Here's the one person who got 28. Okay? Now, we've got two views in SPSS, and you can see here, highlighted in the bottom left-hand corner, I'm looking at the data view, and next to it we've got the variable view. Now, I'm going to go into the variable view, because here you can see the name is score, type is numeric. I've told it to have a width of 8 units. No decimal places, because our scores have no decimal places. I've told it what it means. The label is score. Okay, and here is the critical one. Look at this, the measure. I've highlighted that for you. Can you see it says scale? Now, if I click on scale, you can see there, scale, ordinal, nominal. And I have to tell my program what kind of a unit this thing is. And I'm telling it, because it's a test score, that it's scale. Right, I'm going to go back down now and go back to data view. So I've got all my scores here, and what I want are the mean and standard deviation. Now, if you remember, the mean and standard deviation are the descriptive statistics that describe the curve of normal distribution for this particular data set. It's created, though, from a sample of learners that we use in the pilot, and we have to assume that these learners are representative of a larger population of learners who would take this test in the future. If they are not representative of the larger population, then we could not generalize these statistics to the larger population, and the data would be largely useless. Now, how do we get the mean and standard deviation? At the top, can you see Analyze? Okay. I click on Analyze, and I go down to Descriptive Statistics. When I go along, I get another set of menus, and I want descriptives. And I click on descriptives. So it's Analyze, Descriptive Statistics, Descriptives. Now you can see that it recognizes that I have one variable which is called score. I transfer that into the variable window by clicking on this arrow. I can move it backwards and forwards, but I want it in there. Now, if I just look at the options by clicking on that top box, it says, give me the mean. Here's the sum. You probably don't want that, but you remember at the bottom of the first column, and it was the sum of x, sigma x. If you want that number, you click on that as well, but we don't want that. We want the standard deviation as well, the mean, the standard deviation. We want the minimum score and maximum score, which was 1 and 28, you remember that? And you remember I told you about the range as well. If you want the range, you can click on range and it will give you the range. I then click continue, and down here all I need to do is click OK, and it does its magic. And here we have the descriptive statistics. Score, n equals 25. Range is 27. Because the minimum is 1, the maximum is 28. The mean is 11.72, and the standard deviation is 7.46. So you get everything you need to describe your test results in one table, and you can right click on that, you can copy, and then you can paste it directly into your Word document. So that is how you calculate the descriptive statistics in SPSS. Now, I'm going to go back to my score because I want to show you how to do one more thing, which is kind of moving into research areas, but I mentioned it right at the beginning, and it also helps to explain how you look at variables and you compare the means or the averages between different groups to see if there is really a difference. Now I'm going to go back into the variable view and I'm going to create another variable. So I'm going to click on my second variable and I'm going to call this gender. This is potentially a dangerous one these days, but I am going to assume that this is not particularly problematic. I'm also going to call the label gender. When it comes to scale over here, I'm going to make the assumption that this is a nominal variable. That is, biologically you are either male or female. And you will see in the applied linguistics that this category is exceptionally common. What researchers are often doing is saying, is there a difference in scores or whatever between the girls and boys in my classroom when it comes to reading, for example? You remember the example I gave you right at the beginning. You make an assumption that on average girls are slightly less tall than boys. If I went and stood on the steps of the Charles Wilson building on the Leicester campus and I measured the heights of 100 boys and 100 girls, I would be able to put them into a spreadsheet like this and find out if there was really a difference. Okay, so I've labelled that nominal. I'm going to go back to data view. Can you see now here that I've got score with a ruler and I've got gender, right? And I've got the nominal symbol. Now, I'm going to do something, this is invented data. So what I'm going to do is I'm going to randomly assign one of two genders to each score. And I'm going to do it alternately. And by doing it alternately, there will be no difference between boys and girls, because as I go down, a boy and a girl will get each score kind of equally. So 1, 2. Oh, can you see what I've done here? That's silly because I've left in 2 decimal places. So I will go back to my variable view. There it is, can you see? Decimals 2. So I'll click on that, none, and I'll go back to my data view and the decimal places have gone. Okay, I'll carry on. 1, 2, 1, 2, 1, 2, 1, 2, 2, 1, 2, 1, 2. There we go. So I now have 25 cases and I've assigned a gender. Let's say that girls are 1 and boys are 2. Okay? Now, how do I compare boys and girls to ask the question, on my reading test of 30 items, are girls, I could have a hypothesis, girls are better at reading than boys. Okay, so now I go to Analyze and I go down the list of statistics and I find Compare Means. Now I've got the scores from boys and from girls. This is independent because the two scores are the scores are independent of each other. So I go to an independent samples t-test, and this asks the question, is the average between two completely different groups on the same test different or the same? If I had, say, scores on reading and writing for just boys, and my question was, are boys better at reading than writing, that would be a paired samples test because the scores are paired. I have a boy who takes both a writing and a reading test, and I'm saying, is this person better at reading than writing? So the scores are paired. But in the case I'm giving you, it's independent because one set of scores is from girls and the other set of scores is from boys. I click on independent samples t-tests, and now I have score and gender. Gender is nominal. The test variable is the score, and that must be a scale score, and it must be normally distributed. In it goes. The grouping variable groups nominal category. So I put gender into the grouping variable. It now says gender question mark, define groups. I click on define groups, and remember over here I've got gender 1, 2. I could have said girls, boys by redefining it not as numeric but as using words. I could have just typed in male and female. Group 1 is 1, which is boys, girls. Group 2 is 2, which is boys. Continue. Right? And now you can see it says grouping variable gender 1 and 2. If I click on options, it says the confidence interval is 95%. What that means is I want to be 95% certain whether or not there is a real difference between boys and girls. And that's what it means in the research literature when you see p equals 0.05. Because 95% certain, 1 minus 95 is 5%, or 0.05. Okay, so I just click on OK now, and it does its stuff. And we get another table, and it says independent samples t-test. And what we do now is we look at the significance, okay? And the significance tells us whether or not there is a real difference between the scores. And the score here, 1 is girls, average for girls is 11.92, and the average for boys is 11.5. You can see how close they are, and the standard deviations are also very, very close. So it's unlikely that there will be a significant difference between boys and girls, and that's not surprising because I went 1, 2, 1, 2, 1, 2. So when I look at the significance, it tells me down here significance is 0.610, so there is no significant difference between those two means. The slight difference that we observe is down to just pure chance. For it not to be pure chance, that is a real difference between boys and girls, the level of significance would have to fall to 0.05 or lower in the significance column. Okay? So that explains how we calculate the mean and standard deviation in SPSS, and how we compare the means for two or more groups if you want to introduce a nominal variable. We're now moving on to item analysis, which initially covers two areas, and that is difficulty, the difficulty of the item, and the discrimination, and that is the extent to which it separates the students who are better or stronger on the construct that we're attempting to test, and those that are weaker. We do this usually using software, and you can go to the web page and download the Excel files that we've created for you to do this analysis. Now, you can scan it if you want to, or you can just make a note of the URL so that you can put it in a browser and download it in a short while. You will notice that it is an Excel file. The reason I'm giving you Excel files to do this part of the analysis is because this just isn't available in SPSS. This is too specific to testing for it to get into the more general programs. On the website you will see descriptions of what these are, and suggested reading if you want to read more about how we calculate this. So when we are talking about item difficulty or discrimination, we talk about item facility, that's IF, or item difficulty, ID, and in the literature you will see both of these terms used, and they are identical. The most common method of establishing discrimination is the point by serial correlation, and I'm going to just explain both of these to you before I demonstrate them. Item facility or item difficulty is nothing more than the proportion of students who answer an item correctly. The reason we report this as item difficulty or item facility is that we assume that when we pilot our tests, the sample is drawn from the population more or less randomly, so that they are representative of the students who will take the test in the future, as I've said before. And that means that we assume that in any future administration the item facility or difficulty would be roughly the same, give or take a bit of error. If over time we find that that does not hold, then we have to renorm the test by repiloting it, because something has changed in the population. It may be that the students' teaching has improved, materials, learning has improved, and therefore the test items become easier, and you may then wish to introduce more difficult test items to achieve better discrimination. Okay, the point by serial correlation, usually in the literature, is written RPBI, and that just R is normally used as the symbol for a correlation, and PBI just stands for point by serial. The point by serial correlation is essentially a measure of correlation between one measure, which is a scale, and in this case it's the test score. You remember, it's a scale, an interval scale assumption, and a second measure, which is a yes or no. It's by serial. In other words, it's answered correctly or incorrectly. So it's a nominal variable. So a biserial correlation asks the question, if this person got this item right, did they tend to get a higher score on the entire test? And that is a measure of discrimination. So if learners tend to get lower scores, then they're going to answer more items incorrectly. What we want to know is which of the items contributes most to that discrimination. It is possible to get an RPBI which is negative, and that means that more students who get a low score on the whole test tend to get this item correct, whereas students who get a higher score on the whole test tend to get this item wrong. Now, if that's the case, there's something seriously wrong with the item, because it's benefiting the weaker students. So a point biserial all correlations run from -1 to +1. +1 means that it's perfect correlation. That means all the better students answered the item correctly and all the weaker students answered it incorrectly. 0 would be it's not doing its job, it's purely random who answers it right and who answers it wrong. And -1 would mean that all the better students answer it incorrectly and all the weaker students answer it correctly. So that's our preferred measure of discrimination in classical test theory. Now, what I'm going to do is show you how the Excel file works so that you could analyze your own test data. Here is a copy of the Excel file. I've simply saved some test data in here, and you will see this is fairly straightforward. We have the item number across the top, item 1, 2, 3, 4, 5, 6. I've got 10 items, but you can keep on going. Coming down the side, we have students starting at number 2. So here I've got 2, 3, 4, 5, 6, 7, 8, 9. So I've got 8 students. 1, 2, 3, 4, 5, 6, 7, 8. There we go. So I've got 10 items and 8 students. We would never ever have only 10 students taking sample items because the item statistics would not be stable. Sometimes people say, what n size should I have? How many students do I need to do this calculation? The rule of thumb which we give to our MA students is try and get, well, as many as you can, but 30 is the rule of thumb. And then why 30? It's because at 30 we tend to start getting normal distributions in our sample. But this doesn't matter. I'm only doing this as an example for you, but if you were to do it, the more items you have, the more students you have take the test, the more stable the estimates you get, and then you know which items are working statistically and which are not. Okay, so in each of the cells for each person, I just put a 1 or a 0. The 1 means that they answered the item correctly, and the 0 means they answered the item incorrectly. So our first person, who is labelled 2, because we're using the top 1 as the item number, got item 1 correct, got item 2 correct, and we can read across item 5 incorrect, correct, correct, incorrect, correct, correct. And that's the same for each student. When you have finished inputting your correct, incorrect data, because multiple choice items are designed that way, they are correct or incorrect, we go down through the blue zone, and I'm just scrolling down. You can see how many people we can have in this spreadsheet. a lot. And when we get down to the bottom of the blue area, you can see the item numbers, and you can either read it across the top for item 1, 2, 3 and so on, or you can read it down the side for item 10. I'll read it down there. At the top you've got the proportion correct, which is the IF, okay, or the proportion wrong across there, which is not in the table here, or the point by serial correlation across here, which is the same as the number here. Now I'll concentrate on this section, okay, that I'm outlining. So item number 1, the item facility is 0.625. We round that up, so 0.63, that's 63% got this item correct. That's a good value, you know, it's not too easy, it's near the middle of the range. The more items we get around 0.5, the happier we are, because that means that they're discriminating right in the middle of the distribution. In other words, they strengthen the information that we're getting from the test. And the rationale for that, you will see when you look at the section on how to construct multiple choice items on my website, you'll see the explanation of why items around 0.5 tend to be good. But we do want a spread. We don't want them too difficult. We don't want them too easy, but we want a spread so that we do get discrimination. Okay, RPBI is good, 0.59. Any RPBI above 0.3 we accept and we say this is pretty good, this is discriminating fairly well. Anything below 0.3 we have to ask why. So if we scan down the IF column, 4 and 5 are working really, really well there. They're right in the middle. So is 8, you see. And when we scan across, we're also getting good RPBIs, good discrimination. Do we have any that are too difficult? No, we don't. 2 that are quite easy, 7 and 9. We might want to look to see if the distractors are working well in those 2 items. Looking down the discrimination, we've got 2 here that are not discriminating very well. We've got item number 7, which is only a point by serial of 0.27, and we've got number 10, which is a point by serial of 0.23. Again, we would want to look at those 2 items and we want to say, why is it that some of the weaker students are answering this correctly? There are a range of ways we could do that. We could look at the item itself, whether or not the distractors are working well, why we could actually give the item back to a number of the weaker students and say, tell me why you selected this answer. We could collect verbal protocol data, and that would help us to start discovering why this item isn't quite functioning as we would like. So this is the item facility and point by serial spreadsheet, and all you need to do is to fill in your 0s and 1s, the correct and incorrect from your items. Now, I said there that when we get statistics that look as if there's something wrong with the item, either they're too easy, they're too difficult, or they're not discriminating, we then go on to do distractor analysis. You will remember in multiple choice items, we normally have 4 options in the multiple choice item, one of which is the correct option, and we call that the key, 3 of which are incorrect, and we call those the distractors. And sometimes it's because distractors are not distracting. And so we go back and we say, why are they not distracting? And should we rewrite them and pilot the item again? And sometimes we repilot and we get much, much better statistics. Here is the download page for the Excel file to do distractor analysis. And the simple message here is that distractor analysis is critical because it helps us to maximize the information we're getting from each item. And good distractor, maximizing information by having good distractors improves the facility value and the discrimination. So here is the code to scan to go to the web page, or the URL which is on the screen that you can type into a browser, and then just click on the icon that says Excel download and download the Excel file. I'm now going to put up the This is the distractor analysis example that I've got, and it's very similar to the previous spreadsheet. We have a blue area, but this time it starts at B1. And all we do here is down the side, remember, always down the side are the cases. So 1 is student number 1, student number 2, and so on, or test taker number 1, 2, and so on. And then for item 1, which is B, in this case, we've got 1, 2, 3, 4, 5, 6, 7, 8, 9, 10 items, B to K, this goes on. And then the response that each person made to the multiple choice item. So person number 1 for item B selected A, person number 2 selected A, person number 3 selected C, person number 4 selected A, and so on. You can see from the number of A's, we would expect that to be the key. If it weren't the key, we would be very, very worried. So all we do is put A, B, or C, or D into each of the cells. And when we've finished putting the information in, again, we would want more than 10 items, we would want more than 10 students in a pilot. We then scroll down. You can see you have a lot of students here taking it, if you can get that many. And we scroll down to the end, and down here we've got the number of responses to each item, the number of A's, the number of B's in each item, the number of C's, the number of D's, and then the percentage. And you can see that the percentage, because I've got 10 items, we've got 10 A's for that, the first one, and so it's 0.7. What we want to do here is to scan this table and look for items where there are, for example, this item, item 4, no one answered C. Again, in this item, no one answered B. What we would want to do here, and this, going back to the previous analysis, where we found that there were items that didn't have good point by serials, it could be that these are the items that don't have the good point by serials. We would want to go back to these items and say, why did no one select those distractors? Can we rewrite them? We may also wish to look at the items where only one person answered a distractor and say, well, if we have a large sample size and only one person selects it, perhaps it isn't distracting enough. And we then start to say, well, can we improve our item by rewriting those distractors so that they're still incorrect, but they are a little bit more plausible. As we improve the items and the distractors, our statistics improve for the whole test. Now, there is another video in the section on reliability, which is further down the page on Blackboard. And all of these statistics, as we improve them, also improve reliability. That's the end of this introduction to statistics for testing and assessment. So what we've essentially covered is the mean and standard deviation, which are the descriptives, so-called descriptives. We've covered mean standard deviation, and we've covered the basic statistics that we need for item analysis. Further down, there's one more lecture, one more class on reliability. I hope that this has helped to demystify some of the statistics that you read about in the unit in the course book, and the statistics that you will come across inevitably in the language testing literature and the applied linguistics literature.